Guys, your name tags. All right, let me begin. It's 8:34, so I start a few seconds early. We're going to continue our series of lectures on recurrent neural networks. Specifically, we're going to look at the kind of models that will take in sequences of inputs and generate sequences of outputs. So we already saw some of this in the last class. We're going to continue on the same topic. But here's the general problem of sequence to sequence conversion. You have a sequence going in and a completely different sequence coming out. And the length of the sequence that goes in may not be the same as the length of the sequence that comes out. So like speech recognition, speech goes in. You might have 1,000 vectors go in over 10 seconds of speech, maybe 40 words come out. Or machine translation, a sentence in English goes in, a sentence in French comes out. Or dialogue systems. This is actually a sequence to sequence conversion problem, where you ask a question and the system responds. It's actually converting your sequence to a different sequence. So this is still just a sequence to sequence conversion problem. Or question answering. You ask a question, the network gives you an answer. Again, this is a sequence analysis problem. So recurrent neural networks are useful in all of these kinds of different scenarios. You have different situations. The one that we looked at in the last class is one where there was some kind of an order correspondence between the input and the output. So for example, if you're performing speech recognition, then you have some waveform go in, and the output may be, I ate an apple. Now, it's this order correspondence in that if I slice the waveform and moved portions of the waveform around, the output is going to change, right? But more importantly, the first word represents the first initial portion of the waveform. The second word represents the second portion of the waveform. The third represents the third portion of the waveform. The fourth represents the fourth. So the output order is strictly related to the input order. You can also have other situations like machine translation. I ate an apple. Ich habe einen Apfel gegessen, and in German, slightly bad translation. But then if you look at that, here, there is no order correspondence between the input and the output. The first input word is the first output word, but then ate actually splits into two words on the output. So, and the length of the output, in fact, can be greater than the length of the input. These are two different kinds of scenarios. Or even, in fact, the output may not even seem related to the input. For example, if you had a dialogue system and you said, my screen is blank, the response may be, please check if your computer is plugged in. There's no apparent relationship between the two. So these are all different kinds of scenarios. We are, of course, looking at the first one. That's what we were looking at in the last class. That's what we're going to continue looking at in today's class as well. So here, this was the situation. The output and input sequences happen in the same order, but they may not be time synchronous. The outputs are intermittent. And so, for example, in speech recognition, you have speech going in at various points of time. You say, okay, I've recognized this phoneme. The problems we saw was how to perform inference on such a model, how to output such a time asynchronous sequence, and how do you train such models, right? And we sort of partially addressed this. We will revisit this. If I have a model of this kind, how do you output the right intermittent sequence? We were focusing on how to train these models. And if I gave you the alignment of the output to the input, by alignment, I told you exactly at which instance of time each of these symbols were output, then we knew that we could just sort of replicate the symbols and make this order-aligned sequence a time-aligned sequence by replicating the symbols to fill in the holes. And now you can just define your divergence as the sum of the individual divergences at the different times. And that, of course, is going to be minus of sum over all time, the log of the probability assigned to the target symbol at each time. So this was something that we saw in the last class. And so now if I take the derivative of this, in order to perform back propagation, I need the derivative of the divergence with respect to the output of the network at each time. And so the derivative of the divergence with respect to the output at any time t, there's any yt, is simply going to be log of the rest of the time instants don't matter, right? And so you're simply going to be looking at the derivative of minus log of the probability assigned to the target symbol at that time. And so the derivative vector for the derivative of the divergence with respect to any given yt is going to be a vector of zeros, except the one term corresponding to the target symbol, for which the component is -1 over the probability assigned to that symbol. So this is all things we've seen. Now, the problem we looked at is, how do we do this if you're not given the alignment? And so here we figured that what we can do is to guess the alignment. I sort of initialize a model, or maybe initialize some alignments, and then train a model, estimate the alignments, use the alignments to go back and retrain the model and repeat the process. And that's going to lead to our first poll questions. This one's got to be easy. So I'll stop in 10. Pardon me? Something wrong with the poll?
Same question.
Okay. So maybe, okay, all right, doesn't matter. What is the first answer to the first question? Adnan.
It's false because nobody computes the divergence, it just computes the alignment.
What are you going to do with the alignment?
Compute the divergence.
Thank you. Right? So what about the second one? Namrata, what about the second one? All right, both of them are true, right? So now let's go on. The problem with this approach we saw is that it's heavily dependent on the initial alignment of the initial model. It can take you to bad places. So you may end up misaligning everything, learn a model that's sort of tuned to that misalignment and stay there forever. And so the alternate is don't commit to an alignment in the during any pass, average over all alignments. And how do we average over all alignments? We're going to consider every possible alignment, but each alignment is going to be weighted with the probability of that alignment as computed using the current model. So remember how we computed the found the alignment. If I had a symbol sequence, I pulled out the rows for that sequence, and I made this new table, compressed table, right? And then we found a path through this, the most likely path through this table, and then the divergence was computed with respect to this most likely path that we assumed was the actual ground truth. And so here is the key piece. The divergence is the negative of the sum over all time of the log of the probability assigned to the aligned symbol at that time, right? Keep this in mind. Now, here's a different way of thinking about it. Every path through this trellis, through this graph, has a probability, correct? And so basically every alignment has a probability which is basically proportional to the products of all of the symbols in the alignment. So I can say that there is actually a probability distribution over alignments. Every single alignment has a probability, correct? And what am I doing over here? I'm choosing the most probable alignment. That's just the mode, right? The mode is the most probable term. What is the alternative? I can take the mean, correct? So if I were to take the mean, and so just drawing the most probable alignment and computing the loss on that, I can take every alignment, compute the loss on that alignment, and weight it by the probability of that alignment. That making sense to everybody? Right? And so you guys at the back, that making sense? Okay. And that's basically what we are going to be doing. So instead of only selecting the most likely alignment, I'm going to take the statistical expectation over all alignments. And what is the expectation over all alignments? For any given alignment, the loss is the sum over all time of the negative of the log probability assigned to the aligned symbol, right? So I'm going to be taking the expectation over this term, which is minus of sum over t log y st, right? Which is the aligned symbol sequence. And now, using the expectation, so again, just to drive the point home, if I have, say, two alignments, suppose I had something that was 3 symbols long, 3 time steps long, and I had two symbols A and B in this order, the possible alignments are going to be ABB, AAB, correct? Those are the only possible alignments because I need to have both. And so what I would do is to say loss of ABB times probability of ABB, correct? Plus loss of AAB times probability of AAB. That's going to be my new loss. Making sense, right? So, but then this loss is simply going to be minus of, loss of A plus, this is minus of log of PA at time 1 plus log of PA at time 2 plus log of PA at PB at time 3, right? Because what we found was the loss assigned to any particular alignment is the sum of the negative of the sum of the logs of the probabilities assigned to the individual symbols. But then the expectation is a linear operator. The expectation of a sum is the sum of the expectations. So I can move this guy in, right? But before that, here's another poll. Okay, 5 seconds. This is easy. Okay, Shravan, first question. Rohan, second. False, okay. True and false, right? Easy. So the expectation of a sum is the sum of an expectation, correct? Which means I can say that the expectation of minus sum of log yt is the sum minus of sum over t expectation of log yt, okay? What does this second term mean? So if you look at this, I've drawn what did I do with my chalk? We have drawn a trellis of this kind, something of this kind. Maybe if I have 3 symbols, then, so at this time, I have, it's badly drawn, I have 3 possible symbols, correct? So what do I mean by saying the expectation of the log of the probability assigned to the symbol at each time? So this means you have to take the sum over all of these guys, right? And you're going to say, what is the log probability, negative log probability over here, times the probability of this term, plus negative log probability of this over here, times the probability of this term, plus the negative log probability over here, times the probability of this term. But what do I mean by this crazy, the probability of this term? So this is what it means, right? It's going to be the negative log probability assigned here times the probability that this node happens to be in a randomly drawn path through the graph, right? So in other words, it's the log probability, there's a minus outside, you're summing over all time, but at each time you're going over the columns and they're adding the log probability of the node, which is the log probability of the symbol over there, times the probability that given the input, that symbol was in the alignment. That making sense, right? And so this guy is the probability of aligning the specific symbol S at time t given the unaligned sequence, unaligned but time ordered sequence S0 through Sk minus 1, and the input. So we need to be able to compute this term, right? What exactly is the term? That is the term, again, that is the probability given all the information you have, namely the sequence, the order aligned sequence and the input. That symbol, the symbol S, that this node, the symbol over here, is in the alignment at this time, right? So that basically is, if I look at the P of S comma T given everything, that is the probability that that symbol S is aligned to the input at time t. So which means that over all possible, that is the total probability of all alignments which align the symbol S to time t. Making sense, right? That's going to be the total probability of the graph shown over here. So if I'm aligning the symbol E to time, what is this, 0, 1, 2, 3, then it's the total probability of all paths that go through this guy, right? But then it's a total given, there's also there's a conditionality. So this probability over here, where's my sword? It's not actually just the total probability, it's the conditional probability, the probability of aligning symbol S to time t given the compressed input and the compressed symbol sequence and the input is proportional to the joint probability of aligning symbol S to time t and the compressed symbol sequence. Why am I doing that? If I take the total probability of all paths at this node, is that going to be 1? No, right? How many of you think it's going to be 1? What is the total probability of all paths that go to the bottom right node? What would it be? It is the total probability of all alignments of S0 through Sk minus 1 to the input, correct? So the probability over here is basically the probability of the symbol sequence, because you're considering every way of aligning that symbol sequence to the input, correct? So the total probability at the bottom right corner is the total probability of the compressed symbol sequence. It's not 1, right? This is going to matter for us. And so the probability of total probability of the subgraph I've shown is the total probability of all that you have S0 through Sk minus 1 as the symbol sequence, and that in the process of having this symbol sequence, that E is aligned to time 3. Making sense? Right? So, but this is the term we want to compute. What we really want is, we want the conditional probability. You're given the symbol sequence. I know this is the hello, how do you do sentence, right? What this is computing is the probability that it's hello, how do you do, and that the word hello ended at time 3, right? So how do you convert the one to the other? You would, yes. And what is that going to give you? You would divide, right? P of alignment and the symbol sequence divided by the P of the symbol sequence should give you the P of alignment given the symbol sequence. But that's for now, right? What we really are interested in is the probability of the subgraph, which is the total probability of, which is the probability of aligning symbol S to time t and the larger sequence, okay? So how do we compute the probability of the subgraph? This is the challenge. Now there are an exponential number of paths potentially through this graph. So you can't just be explicitly adding over the entire lot of them. So what will we do? We're going to chop it up into 2 parts. Everything from the beginning node till that node, and everything that follows that node all the way to the end, right? So there's the event of aligning. So what does the left side of the graph tell you? The left side of the graph is every way of aligning B to the first four inputs, correct? And the second portion of the graph There's every way of aligning. Now that's a little more complicated. Either E, F, E, or phi, right? To what followed, right? So so now given this, I can say that the probability of but by Bayes' rule, since I've decomposed it into two subgraphs, the total probability of the pink graph is the probability of the graph in blue times the probability of the graph in red given the graph in blue, right? That's Bayes' rule, right? And here we're going to use something called conditional independence, right? The conditional independence. So does it matter to me what, so long, if I'm telling you that at time 4, you're going to be in one of those two nodes, right? Does the actual alignment from time 0 to 3 have any influence on that probability? It doesn't really. Why? Because if you think of how you look at the probability tables, when I was using the recurrent network to compute the probability table, the way you did it is you took the input went through the hidden layers, and from the hidden layers you computed the probabilities, correct? So basically, you didn't care about how the initial portions of the network, of the symbol sequence were aligned. You didn't say that at time 3, I'm aligning this to E, and use that information in computing the probabilities at time 4, right? The probabilities at time 4 were dependent only on the hidden state deterministically. They did not refer to the alignment at time 3. So in other words, what we can say over here, and that's simply because the hidden states are all deterministically computed, right? The hidden states are just dependent on the input. They are not the hidden state, so the probabilities output at any time do not consider anything that happened at any other time, the probabilities at other times. They only look at the hidden states, right? And so therefore, instead of saying that this blue portion instead of saying the probability of the red portion of the graph times the probability of the blue portion of the graph given the red portion, I can simply say it's the probability of the blue portion of the graph times the probability of the red portion of the graph, because there's no conditional dependence between the two, right? And so I can just so I'm going to call the first portion the forward probability. I'm going to call it alpha RT, which is to say the probability of aligning the rth symbol to the tth time instant. And the second portion I'm going to call the backward probability, which is the probability of everything else that follows given or in that the rth symbol has been aligned to time t, okay? So let's look at what this guy is. What is alpha TR, right? Did I call it alpha RT or alpha TR? Alpha TR, okay? So what is this probability? How do I compute the probability of aligning everything on, this portion of the graph, the probability of aligning the first two symbols such that the rth symbol is aligned to time t. So if you look at this, I can get to the YE3 from one of two places, right? I can either get to it from from B2 or E2, okay? So in other words, if I consider all possible ways of aligning E to 3, I can either do it by aligning B to 2 and then and then patching in E to 3, or I can do this by aligning E to 2, which is the second portion, and then following it by E3, right? So if I look at the total probability of all paths that end here, I can either go here, there's a total probability of this subgraph followed by this guy, plus the total probability of this subgraph followed by this guy. Right? Are you seeing what I'm talking about, right? But then the total probability of this graph here is alpha E3, right? Or alpha 3E, I don't know how I've written it. What is this guy? Pardon me? Alpha 2B, right? So this first portion is now going to be alpha 2b times y, ye3, correct? What is this guy? Alpha 2e followed by this guy. So basically, if you look at this, it's this alpha over here is the sum over all predecessors, all parents of this node, of the probability of the subgraph ending at that parent at time t minus 1 times the current probability, which is simply going to be the corresponding alpha, right? And so I can just say that the alpha at any tr is the sum over all parents of the node of the alpha of the parent times the probability of the current node, right? This making sense, all of you guys, right? So this makes it very simple. Now, once I have this recurrence, I can compute my alphas very simply. So here's the overall probability. The total probability of the subgraph shown, which ends at symbol, the rth symbol at time t, is the total sum over all predecessors of RT, all parents, of the alpha at the parent times the current node probability, right? So now I can use this. In our graph, every node has only two parents, right? At tr, you have one parent, which is t minus 1, r minus 1, and the other is t minus 1, r, correct? And so I can say alpha tr is alpha t minus 1, r plus alpha t minus 1, r minus 1 times the probability of the current symbol. Everyone with me? Right, so now I can start from the beginning, right? In the first column, I know that I'm only allowed to begin at the top node. I'm not allowed to begin at the subsequent nodes. So the top node alone has if you look at all paths ending at the top node, that probability is simply going to be yb0 over here. If you look at the total probability of all paths beginning at subsequent nodes, they are not allowed. So they're 0. Correct? So now I have computed the alphas for the entire first column. For the top left, it's simply the node probability. For the rest of them, it's 0, right? Then I can take a step forward. And over here, for every node, all I'm going to do is to say, as I can go from top to bottom. For every node, I sum up the alphas of the parents and multiply the node probability. And so here you would find that you're going to get valid alphas for the first two guys. But for these two guys, both their parents have 0 probability. So you're going to have alpha equals 0. You don't have to take any special cases. Simply by initializing the alphas to the black entries as 0, everything works out, right? And then you can go to the next time instant. And for every node, you can go down the list, go down the column. And then for each node, you're simply going to sum the probabilities of the two parents, which is t minus 1 r and t minus 1 r minus 1, and multiply the node probability. And you can keep doing this going forward all the way to the end. And so when you go forward, you're going to compute alpha so you're going to get this alpha probabilities for every single node in this table, every single node in the graph, right? So which means that I have computed, and now here's the best part. If you actually do this, when you get to this final node, this is the total probability of all paths through the graph which align B phi to the input, right? So what is that? That's going to be the total probability of B phi, period, right? Because it's every possible way of aligning B phi to the input. And so that's the total probability of B phi given the input say x's, okay? But moreover, in the process, that first term has been computed for every single node in the graph, right? So now let's look at the second term, which is this guy. What is this one? Now this is a bit funky, right? Because if you look at the first column of this subgraph, it has multiple entry points, right? And so it gets a little bit complicated, but here's how I can simplify it. I'm going to extend it by including the initial node itself. Later on, I'll delete the initial node. Okay? So the probability of this blue subgraph is the probability of the entire graph that starts from the orange node. Correct? So this is the probability of the exposed subgraph, but not including the orange node itself. Correct? I'm going to include the orange node just for convenience sake. Once I include the orange node, I'm going to get the total probability of the subgraph including the orange node. But if I want to eliminate the orange node eventually, I just have to just divide this guy by the probability of the orange node, and that gets eliminated. Right? Everyone with me? Right? And so the beta hat is the probability of the graph that includes the orange node. Beta is what you get when you divide this by YTSR, right? The probability of the node. Okay. So now we just need to find an algorithm to compute the beta hats. And does this look familiar? Here's what it is. The total probability of all paths starting from the orange node going to the end can be decomposed. The orange node has 2 children in this case, right? So the subgraph that starts from the orange node and goes to the end either goes from the orange node to the first child, and then it's the entire graph that follows, or from the orange node to the second child, and the entire graph that follows. Right? Now this guy here, this top one is beta hat of 3E. Correct? What is this one? This is Y3E times beta hat of Y4E, right? What about this one? Say Y3E times beta hat of, right, Y4E. So you see how that whole thing works out, right? Y4F, and that was Y4E, right? So I can just say the beta hat at 3E is Y3E times the probability of the subgraph starting at 4E plus Y3E times the probability of the subgraph starting at 4F, right? Which, as we know, are simply beta hat 3E and beta hat 3F. And now, magically, we have our recursive algorithm. Except now, so here's the overall probability. Beta hat at any TR is YTSR times the sum over all the children of that node of the beta hat at those children nodes. Very trivial algorithm, correct? And then from beta hat, eventually you want to get beta. So what you're going to do is you're going to divide beta hat by TSR, right? Just the node probability. But then given this, here's the entire backward algorithm, right? I can start from the rightmost column, and I can say that the beta hat for the bottom right row node, which is where the graph must end, is going to be the node probability, right? For the rest of them, the probability is 0, right? Everything above that bottom right node has 0 probability. That's how you initialize it. Then I can take a step back. So this is how you initialize it, right? Then I can take a step back, and then I can just compute the beta hats for these guys. For each node, I'm going to sum the beta hats over all the children, and then multiply in the node probability itself. And so going from top to bottom, I can compute the beta hats for the second last column. Once I've done that, I can take a step back and do the same thing for the third to last column. For each node, I've already computed the beta hats for all the nodes in the next column, right? So I know the beta hats for all the children. I can just sum up the beta hats for all the children and then multiply in the node probability. And so now I have the beta hats for all of these guys, and I can keep going backwards till I have the beta hat all the way back to the beginning, right? But these are the beta hats which included the node probabilities. To compute the actual betas, you've got to divide by the node probability. That's it, right? And so now we have figured out, so that's just the pseudocode. Your initialization is going to have the node for the beta hat. There's the node probability for the bottom right node, 0 for everything else. And then you're going to keep going backwards. And at each time you go down the column, for each node, you sum up the beta hats for all the children and then multiply it by the node probability. Very easy. Finally, when you're done, you divide to get the actual beta from beta hat, you divide it by the node probability, right? So now we know how to compute the probability of the blue graph, and that's what you're going to represent using beta. The algorithm which computed the alphas is what we'll call the forward algorithm, Alpha is called the forward probability. The algorithm that computed the betas is what we'll call the backward algorithm. Beta is called the backward probability. And now the probability of alpha times beta is the total probability of the graph, including the red and the blue, right? So if you ask me the total probability of the subgraph that goes through any node in the table, all I need to do, first I compute the alphas for the entire table, then I compute the betas for the entire table. Then if you want this term for any node in the table, I just pick up the alphas and the betas and multiply them, right? But here's an issue. What I want is the conditional probability. For my expectation, I want the conditional probability, right? We said over here that I want the log probability over here times the probability that an alignment goes through that node, right? So when I speak of an alignment, it is given the input sequence, whereas this is the joint, right? Alternately stated, if I go down any column, so if I'm looking at the conditional probabilities, the sum of the probabilities across this column must be 1, right? Alignments either go through this node, or go through this node, or go through this node. There's no other option, right? So the probability that alignments go through this node, plus the probability that they go through this node, plus the probability that they go through this node, that is going to be 1, right? Will that be the case if I simply sum up the alpha betas across a column? Will it be the case? Shravan? Yes or no? Can everybody just say no together? There are not many people in the class. I want to hear aloud no. No. Okay, why no? You said a very enthusiastic no, so why no? Right, so what happened? That alpha beta, this is the probability of that you have got this symbol sequence S, right? Think of it as some random process. I could be, at each time, the network has given you a probability over all symbols, right? At each time I could pull any symbol. If I take a whole bunch of symbols randomly drawn, what is the probability that that symbol sequence is going to compress to S? That is going to be the total probability at the bottom right corner, correct? So this term over here is the probability that if I just randomly pull a symbol sequence, I'm going to get capital S as my symbol sequence, and that the small s is aligned to time t. Correct? So this one over here is the probability alpha, the product of alpha and beta over here is the probability that I got this symbol sequence and the symbol over here was this thing, right? This is the probability that I got this symbol sequence and the symbol over here was the second symbol. And so also this. If I sum them all up, what do I get? Can you say that aloud? Total probability of what? Which is? So what does it represent? The capital symbol S, right? So here, for example, if my symbol sequence was AB, right? So, or if I had some ABC, that's going to be the probability of that I've got ABC, right? So if this represented the symbol sequence ABC, then the total probability of all paths that go through this node is the probability that I got an ABC and the symbol at time 2 was A, right? Everything that went through this node was, I'm aligning it wrong, it should be this way, okay. So if I got this, right? This is the probability that I got an ABC and the symbol at time 2 was A. This is the total probability that I got ABC and the symbol at time 2 was B, right? This is the probability that I got an ABC and the symbol at time 2 was a C. But the symbol at time 2 has to be either an A or a B or a C, correct? You have no other choice. So if I sum them all, I'm just going to get the probability of ABC, right? Regardless of which column I sum it at. Is that making sense? Right? And so, which is also going to be the product of alpha and beta over here, right? Okay, so if I want to convert it to a conditional probability, I have to divide it by PFS, right? And alternately stated, if I look at it this way, the product of alphas and betas at any node is not going to be, if I sum the product of alphas and betas over here, that's not going to be 1, right? But so if I want the conditional probability, I want to normalize it, right? So to normalize it, I'm going to take alpha beta, and then I'm going to sum the product of alphas and betas over the entire column and divide by the sum, and this normalized term is going to be the conditional probability that I aligned the symbol S to time t given the larger sequence, the entire sequence. Is that making sense to everybody? I know you're all sleepy, but raise your hands if it made sense. Very unenthusiastic. I'm not sure you got it, but I'm going to believe you did, okay? So procedurally, you've understood how the forward algorithm worked. You understood how the backward algorithm worked. You understood how to compute alphas and betas. You understood that in order to compute the probability of all paths to a particular node, you just had to multiply alphas and betas. And so simply mechanically, I can go down the column. The products of alphas and betas down the column don't sum to 1. I can normalize them to make them sum to 1. So once I have that, then I'm going to call that my gamma TR, which is the posterior probability that given the symbol sequence, an alignment went through the symbol S at time t. And once I have that for every node over here, right, then I can just compute. So this is, my line is bad. Then at time t, this is going to be the gamma over here times log of this, the log of the probability at this node, plus the gamma here, times the log of the probability at this node, plus the gamma here, times the log of the probability at this node, and you sum this over all time, right? So that's going to be your new divergence. So we got our expected divergence over all possible alignments, and it wasn't a particularly hard algorithm to compute. Very straightforward, right? We didn't have to choose an alignment anymore. And so, yeah. This is easy, 5 seconds more. Okay, Samaran, do we have anyone on Zoom? So, are you tracking Zoom? Someone on Zoom, give me both answers. Is the first one right? Both are correct, okay? Obviously, all right. So we know how to compute the divergence, right? But what we need is the derivative of the divergence with respect to the outputs of the network at each time, right? What is the network outputting? So this gets a little complicated, but if you made more complex by the fact that I lose my chalk, but the network, if you had a network and the network was computing at each time a probability over all symbols, correct? And then from these, you just picked up some probabilities and you form this graph, right? But when I want the derivative of the divergence, I want the derivative of the divergence with respect to this entire probability vector, right? Some nodes in this probability vector did not occur at all in the graph. So clearly for those terms, I'm going to have derivatives for A, B, and C, but for these guys, the derivatives are going to be 0. So that's easy. Correct? Now, I just worry about, so let's just assume that this was an ABA, just for argument's sake. So even C is going to be a 0, okay? Now, I want the derivative of the divergence with respect to the probability assigned to the symbol A at this time, right? But the symbol A occurred twice in my graph, correct? So I'm going to add, this is gamma, this first A, this is gamma 0 at time 2, and this is gamma 0, 1, 2, 2 at time 2, right? So I'm going to sum the gammas at both of these guys and then multiply that by the log probability. That makes sense, right? That's because the node can occur multiple times in the graph. And so if you look at this, I want to compute the derivative of the divergence with respect to the output of the network. And basically, in order to compute the derivative of the divergence with respect to any term, if it doesn't occur in the graph, that's going to be 0. If it occurs in the graph, I'm going to go over all of the nodes where that probability is invoked. And I'm going to take the derivative of the sum, negative sum over all of those nodes of gamma times the log probability, right? And compute the derivative from that. So it's d over dy of gamma tr times log yt, right? But then this one, and so the reason you have the summation is that a symbol can occur multiple times in the graph. Now the question that remains is, what is this derivative? D over dy times gamma times log y, right? So here's the thing. I'm going to take, if I'm just using the chain rule, it's going to be gamma divided by y plus log y times the derivative of gamma. Gamma divided by y is easy to compute. But gamma itself is a very ugly thing, right? So if you want to compute the derivative of gamma, it's going to be a headache. So what is the solution to this? I'll tell you the engineering solution. You come up with an alternative mathematical explanation that doesn't require you to compute the derivative of gamma. And so you just throw it away, right? You just throw away. So the second term, which is the derivative of gamma with respect to y, you just ignore it and you say, voila, this is a maximum likelihood estimate and everybody is happy. So this is basically what we do. This is the happy solution, okay? And so if I want to compute the derivative of the divergence with respect to the probability assigned to by the network to any symbol at any time for a given input sequence, for the terms that don't appear in the sequence, of course, it's going to be 0. For the rest, it's going to be minus 1 over the probability assigned to that term plus the summation over all the nodes where that symbol occurs of gamma. Now you can go back and look at this to what happens when you are actually given the alignment. When you're given the alignment, this gamma is going to be 1 for one of them and 0 for the rest because you deterministically know what a symbol was aligned where, right? Here you're just sort of spreading it out, but otherwise it looks exactly the same. Make sense? Right, okay.
One question.
Yeah.
Why is, I mean, you would want to penalize a network if it's giving you a probability for the symbols that should not occur there. Like in the first row, you should always have a B and not a E, F, and E again, right? So why should the divergence there be, derivative or divergence be 0? It should be some value to penalize the network.
So no, so the point is the rest of the symbols in, like A and Z don't occur, right? So they don't contribute to the divergence.
Okay. It's other symbols apart from BC.
Yes, right. So we are speaking of anything, things that are not in B phi don't contribute to the divergence, right? Yes, okay. So here's the overall training procedure. You're given input and output sequences without alignments to train the models. You're going to set up the network, typically a many-layered LSTM or something else. You initialize all the parameters of the network. And then in the forward pass, you pass each training instance through the network and obtain all symbol probabilities at each time. Then from these guys, you compute the compressed table, which only represents the specific symbol sequence for that input. This is being done for every input, right? Then from this, you first perform a forward pass and compute an alpha at each node. And then you do a backward pass and compute the beta at each node. And then you can multiply alpha and beta and normalize and compute the gamma at each node. And from the gammas, you can now compute the derivative of the divergence with respect to the output yt at each time. So that's going to be the derivatives with respect to each of these columns in the bottom portion, right? And those are going to be plugged in to your standard gradient descent. So everybody clear? Questions? Yes.
Is there any reason for including the target symbol in the forward part of the equation? Like, why can't we break it in the other way where
You could, right? So you could say everything until the target symbol and the target symbol. It doesn't matter which way you do it. Eventually, it's going to be correct, right? That's just convention. Good question. Okay. So sequence to sequence models which irregularly output symbols can be decoded. That's not greedy, that should be greedy decoding. If you want to train them, they require alignment of the outputs to the symbol sequence. And this is generally not given. So training can be performed by iteratively estimating the alignment using Viterbi decoding and then updating and time synchronous training alternately. You can just perform training by optimizing the expected error, expected divergence over all possible alignments, right? Where the posterior probabilities for the expectation can be computed using the forward-backward algorithm. Now, in all of this, so we've seen how to train the model, but we're still left with a very challenging problem, which has to do with the fact that when, if I've got my model and I output my probability table, right? Then from the probability table, I have to decide during inference. Now I'm not speaking of training. During inference, I have the model, right? I have magically trained it. And then I just pass my input. I'm going to get the probability table at each time. From this, I have to decide which word sequence was spoken or which symbol sequence was generated, right? And if I pick the most greedy symbol sequence at a symbol at every time, I can end up with something like this, right? Is this read or is this read? It's not clear, right? It's just a sequence of E's. So we need some way of distinguishing between, we've seen this before as well, right? We need some way of distinguishing between read and read. So what we will do is this. I'm going to introduce an extra do nothing symbol into my vocabulary. This do nothing symbol literally does nothing. Its only job in life is to separate things, right? This is a blank symbol. And so the blank symbol, when I get a time synchronous sequence of this kind, when I compress it, we removed all repetitions and left it with one, right? When I compress a blank symbol sequence, it's going to basically disappear and go away. But now, because the blank symbol is a unique symbol by itself, things on either side remain separated. Okay? And so if I compressed the RRR, blank blank, EE, blank blank blank, DDD, these three R's will become an R. The blanks disappear, the two E's become an E, the blanks disappear, and this becomes a D. Right, okay? On the other hand, if I split this one, I have RR, it's going to become an R, right? The blank disappears, the E remains, the blank disappears. Then after that, I have two E's, they're going to compress into an E, and then the D remains. So this becomes a read, right? Same thing here. I have two R's, so they're going to compress into an R. Then I have a blank. The blank disappears, but it separates the next R from it, right? Because there was an intervening symbol. And so now this R remains, then the blanks go away again. These two E's become an E, the blanks disappear. This D stays, then the blank disappears, the two D's compress to a D, right? So you see what's happening over here. So what would this compress as? Anyone want to tell me? Jessica? What's it going to be? R for, say that aloud, please. Is it R? There are three R's. They're all separated by blanks. So this is going to be somebody else? That's going to be three R's, two E's, and three D's, right? So you get the idea of how this blank works. If it occurs somewhere, it separates the things to the side. Otherwise, things collapse, right? So here's a poem. Okay, this is easy, 5 seconds. Anyone want to take the answer? Jessica, which one is it? Fourth, right? That's the only one that stays. Because here this simply becomes BILY. This becomes BBILLY. This becomes BILY again. And this becomes BILLY, correct? So you see how this works. Now that I've introduced an extra blank to account for this ability to separate things, I don't have to worry about whether things are being repeated or not. It's automatically being taken care of. But now I must also include this in my vocabulary. So my network is now no longer just going to produce the probabilities over the symbols that I will actually be outputting. There's going to be an extra entry in my vocabulary which represents the blank symbol. Here's the odd bit, that when you write down symbol sequences, is anybody writing a blank for you? Are you writing B blank ILLY? So here is a symbol that's never given to you in your training data. Yet you have to learn a probability for it. Right? You see the issue here? But we need it for decoding. So here is this, right? If I have this extra blank at the top, now if I get something of this kind, if I pick the most likely symbol at each time, what is this going to become? It's going to be B, E, F, E, right? It's B, F, correct? On the other hand, if I had this, what is this going to be? This is anyone? This is going to be? This is going to be beefy as well, right? What about this? There's going to be two Fs because there's a blank between the two Fs, right? So you see how this thing works. So I'm going to show you how this works. But now just because I have a really crappy example, I should have been using read versus read. But it was very painful to make these figures. I don't want to spend 6 hours making these pictures again. So I'm giving all of you a really crappy example for the nth time over n semesters. And this is B with 2 E's for some strange reason. But now suppose this is the symbol sequence I want. I have 2 E's in a row, right? If I did it using the original method, where I say I have B, E, E, F, right? And then I just pulled out the rows and made my compressed table. What will paths through this graph compress to? You're going to be missing the second E, correct? You're just going to get biff. So I clearly have to modify this to account for the fact that there are 2 E's. Right? Rebecca, you okay? Yes. So the way I will do it is, now observe that here's something I wanted you to see, that you could get a blank even in the first position. You could similarly also get a blank in the last position, right? And so here is the modified graph. My first symbol could be a blank or could be a B, right? So I'm going to introduce a blank between every 2 symbols in my graph. Instead of just saying B, E, E, F, I'm going to introduce a blank before the first symbol, after the last symbol, and between every 2 symbols. But all of those blank rows are identical because I basically grabbed the top row of this table and copied it in each position, right? Just so. And now here's my graph. My first node can be either a blank or a B, correct? So from a B, the next symbol can either be a B again, or I can go from a B to a blank, or I can go to an E, right? So there are three children. Because if I'm trying to produce B phi, then I can say B blank E, 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 correct? Also, but without the blank, I can just go directly from B to E. So I have 3 children. But then for the blank, if I'm going to this the first row blank must transition to a B because I cannot skip the B, right? The first symbol has to be a B. The second row blank must transition to an E. I cannot skip the E because E is part of the symbol sequence. So from the blank rows, I have 2 children, one going ahead and one going down. Blanks can be repeated, or you can go to the next symbol, right? But then look at the second E. The second E, the first B could go straight ahead, one step down or two steps down, right? The second B can go, E can go, for the first E can go one step up. It can go to the blank, but it cannot directly go to the next E. Because if it went to the next E, then the path is going to just not have a separator between the two E's. And that will compress to just a single E. Is that making sense? Right, you guys there? Is that making sense? Right. And so basically, you're going to be adding edges such that all paths from the initial node to the final nodes unambiguously represent the symbol sequence. So the way to think about it is like so. The first and last columns are also allowed to end at initial and final blanks, right? Now, skips are permitted across a blank, but only if the symbols on either side are different, right? If they are the same, then skipping the blank is going to basically merge the two, which is why you don't have skips from the E row, first E row to the second E row, but you have skips in all the other rows, right? And so now once you form this graph, everything else remains the same, right? I can do my forward algorithm, same as before, except now in the first time instant, I could begin from either of these nodes, correct? And then I'm going to use the same algorithm as before, where I'm going to say that I'm going to sum over all, I'm going to go down the column, and I'm going to sum over all the parents, the alphas over all the parents, and then multiply in the node probability, except that in some cases I will have 2 parents, in other cases I'll have 3 parents. So I'll have 2 parents if the previous compressed symbol was the same symbol, right? So for the second E has is preceded by E. So it's going to have only 2 parents because I couldn't skip the blank, right? But for the rest of them, I could have gone to themselves the blank or the previous symbol. So they will have 3 parents. So I can say that if SR is not equal to SR minus 2, then I have 2 parents. Otherwise, if SR equals SR minus 2, I'm going to have 2 parents, otherwise I have 3. I sum the alphas and then just multiply in the gamma, right? The Y, the node probability. That's what I would do going forward. Similarly, when I'm going backwards, I'm going to have zeros for everything except the final 2 nodes to compute my beta hat. And then when I take my step back, for every single node, some nodes will have, I'm going to sum over all the beta hats over all the children, and then multiply in the node probability. Except that some nodes will have 2 children, some nodes will have 3 children, right? The bottom row has only 1 child. So for any symbol, if the next symbol is also the same, like E is followed by an E, then in an E row, there's going to be only 2 children, right? Because you're not allowed to skip the blank. For anything else, like for burr, then you can go from burr to blank, or burr to E, so there it's going to have 3 children, right? So the simple logic is going to be that for any node, you're going to sum at least 2 guys, and then if the next symbol is not the same as the current symbol, you'll also add in the beta from 2 rows below, right? And then you multiply in the node probability. So everyone with me so far? Rebecca, making sense? Okay, I need an enthusiastic nod of the head. So does this make sense? Guys, you're going to come back to me with during the homework. So raise your hands if it made sense, please. You are not convinced. Okay, where did I lose you? So did that make sense to you? Where did I lose you? You're thinking. Okay, so where? This has to be fairly clear, right? So let me show this. I have a couple of minutes. It's 40, I have 15 minutes, so I'm going to have to rush through things, but I think I can manage. So here's what it is, right? I can say, like, if I'm looking at read, right? From an R, I can go to an R to an R, correct? I can repeat R's. So you there, This was for you. Can you sit here so I can see your face? I'm doing this specially for you, so sit right there. Okay. So if I have something like read, an R can be followed by an R can be followed by an R, correct? I can also have R blank, I can have R, 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 I can have R blank E, I can have RE. These are the three possibilities for read, correct? There's no other option. So R can be followed by an R can be followed by a blank, R can be followed by an E. Correct? But for E, I can have either EE, which is a continuation of the same guy, or I can have E blank E. But so from here, I can go this way. I can go to a blank. But if I go straight over here, it's like I'm skipping the intermediate blank, and this path doesn't have a separator anymore. Right? So if I took this path here, let me try to draw this. Here's the logic. R, E, E, R blank, E blank, E blank, D, right? So if I had and so then suppose I had a path here and I allowed the skip, right? If I took this path, that's going to be R, E, E, and then finally it's going to come to D, correct? So this is going to come out as R, E, E, D. When I compress it, these two E's are going to become a single E. And so I'm going to end up with an R, E, D, correct? The only way I can prevent it is to ensure that there's a blank in between. So which means I'm not allowing a skip from the E row to the next E row. So if the two symbols are the same, I need to enforce a blank in between. Otherwise, I can have the blank be skipped. I don't know if made sense to you, but I tried. Okay, go back and look at the slides. Everything else stays the same, okay? And so now the overall sequence is given input and output sequence without alignments. I want to train models. I'm going to set up the network, initialize all the parameters of the network, but now I include a blank in my vocabulary. And because blanks are introduced in the graph, they don't have to explicitly be actually given in your training instance, right? You just learn the probability for the blank. And then you're going to compute this probability table, compose the graph, perform the forward and the backward computations. From these, you would compute the gammas, obtain the derivatives, compute the derivative of the divergence with respect to the probability vector output at each time, and these can be used in backpropagation. Fairly straightforward, okay? Nothing particularly complicated. So this overall framework we saw is what is called connectionist temporal classification. We still have one more problem left. So I'm going to spend the last 12 minutes on this. This applies to models that are order aligned, but time asynchronous, right? So which means like speech recognition. The output and input have a definite order correspondence. The first output symbol corresponds to the initial portion of the input and so on. But you don't have an output at every time, right? So, but then, this is about training again. Let's go back to the problem of inference. By introducing blanks, I have assumed that I have solved the problem of finding unambiguous outputs, right? But have I really done that? So what if I were to just pick the most likely symbol at each time and then compress it? I will get an unambiguous output, but it's not necessarily the most probable one. So what do I mean by this? Look at this guy, right? Let's say that from this table, I pulled out a bunch of possible time-aligned sequences, right? And the first one was RR blank EED. The second one was RR blank blank ED, and so on, right? And each of them has a different probability. If I just pick the most likely symbol at each time, which of these guys would I pick? The first one. It's the first one? The third one, for the fourth one, right? The TED, because it has the highest probability, 0.71. But then look at the rest of them. I have three possible ways of getting a red, and all of them have approximately the same probability. Whereas for TED, the first one is 0.71, everything else is really low. Given this, which would you choose? The red makes more sense, right? Overall, across all options, red is more probable. Whereas TED has this one outlier, which is very high probability. But if you consider all possible ways of aligning TED, most of them are kind of off. So intuitively, red, even though the most likely red is slightly less probable than the most likely TED, what you really want over here is a red, right? So this is a greedy decode that picks the most likely output, picks TED. A decode that considers the sum of all alignments of the same final output will select red, right? Which is more remarkable? Red is more remarkable. Now, yes, I mean, which is more intuitively correct? Red is more correct, right? But here's a remarkable thing. Because of this, these models are so good that if you just performed a greedy decode, you're not going to see such dramatic changes. Most times a greedy decode will just give you the correct output. And the reason for that is this, that this is from Graves' paper. If you look at the output of the network, you have several symbols. He has plotted the probabilities assigned to various symbols as a function of time. And the dotted line is the probability of the blank symbol. And what you observe is that most of the time, the most probable symbol just happens to be a blank. And the correct symbol simply pops up where it is supposed to pop up, right? So simply getting a greedy decode and compressing it will give you the desired output more often than not. Nonetheless, from a purely theoretical perspective, what we want to do is to find the most probable order aligned sequence, right? Our real problem is I have the speech recognition, the speech recording. Which word was spoken? And when I say which word was spoken, I'm asking you what is the symbol sequence that is most likely given this input, which means I have to consider all possible ways of aligning the symbol sequence, right? Not just the most possible way. So the greedy decode just finds the most likely time synchronous sequence. What we want is the most likely order synchronous sequence, which sums over all possible alignments, right? And this is a challenge because there is going to be any arbitrary number of symbol sequences, and each of them is going to have an exponential number of alignments. How do you compute your decode? So this gives us, for this, first, how do I compute the total probability of all alignments of a symbol sequence to the input? Again, here is the problem, right? I want to find the compressed symbol sequence that has the highest probability given the input. For this, I need to be able to compute this probability term, the probability of the compressed symbol sequence given the input, and we saw how to do that. If I give you a symbol sequence, I can compute this trellis. The probability at the bottom right node is going to give me the probability of the symbol sequence, right? So to solve this problem, I'd have to compose this trellis for every possible symbol sequence, all infinite of them. Compute the alpha for all of them and pick the one which was most probable, right? That's what this problem is really asking me to do. And this is not going to be feasible, right? So this gives us, some of you will know this stuff, the rest of you would have slept through this portion of this lecture, but yeah, this gives us our engineering solution. We want to find the most likely order compressed sequence such that the alpha at the bottom right is highest for that compressed sequence, correct? So I'll give you this poll, then we'll just rush through this. I'm going to go a couple of minutes over. I hope you don't mind. Okay, 5 seconds. Okay, Adnan, first question. All right. And Hojong, second question. Okay. You guys, second question. Pardon me? True? Both of them are true, right? The actual objective is to define or identify the most likely compressed symbol sequence. And finding the probability of a compressed symbol sequence is the same as computing the alpha at the bottom right when you align that symbol sequence to the input, right? So explicit computation, however, is going to require you to evaluate an exponential number of symbol sequences. And this is not going to be feasible. So for this, here's what I'm going to do. I'm going to actually go back and represent my symbol sequences in a smart manner, okay? So let's consider a very simple example. Let's say I just have two symbols A and B in my vocabulary, right? Then I naturally also have to add a blank, correct? So if I look at, so now let's go back and see what we can get when I don't erase the blank, right? Blanks are allowed, so remember when I was compressing everything, I was just sort of removing the blank. Don't erase the blank, keep it there, okay? Because that is part of the decode, right? So the first symbol, I'm just going to start with a dummy, right? The first symbol could be a blank, it could be an A, it could be a B, correct? What about the next symbol? So a blank could be followed by an A. So I'm speaking of after compression, but without eliminating blanks, right? A blank could be followed by an A, or it could be followed by a B, correct? Then an A, what can it be followed by? It can be followed by a blank. It can be followed by a B. It cannot be followed by an A, right? And a B can be followed by a blank and followed by an A, right? But then here's the thing. The blank can follow the A as well. The blank can be followed by an A, right? Both of those represent BA. And over here, this guy, I have this structure, right? So this is representing, so let's just look at the upper portion. A blank can be followed by, if I have two symbols, S1 and S2, either an S1 or an S2, right? S1 can be followed by S2. S1 can be followed by a blank, which can be followed by an S2, right? S1 can be followed by a blank, and then it can be followed by an S1, right? Or it can be followed by and the blank can be followed by an S2. So all possible extensions of S1 are shown by the node on top, correct? Similarly, an S2 can be followed by an S1, or it can be followed by a blank and an S1 or a blank and an S2. This is all possible ways of representing extending S2, right? But then I can repeat the structure. The node that follows, the portion of the subgraph that follows S1 is going to be the same thing following S1 every single time, right? The subgraph that follows S2 is going to be the same thing every single time, right? And so you have this tree-like structure. I'm calling this a semi-tree, which represents all possible hypotheses, all possible symbol sequences in the language, right? If you don't erase the blank. There's nothing else that's not represented over here. But it's a very simple tree, correct? So here's what I will do. I'm going to take this tree over here and draw this on the left-hand side of my graph. I just drew it vertically. I can always draw a tree vertically, right? And now, look at this trellis. From any column, now each node over here, so each node in this tree represents a unique symbol sequence, right? Every node in this tree represents a unique symbol sequence. And so in this, each row over here represents a unique symbol sequence. I'm going to have an edge from any node over here to another node over here. If it's either the same node, so I always have horizontal edges, or if there's an arrow up here. So you can see that I have an arrow from blank to S1, so there's always an arrow going up here, right? I have an arrow from blank to S2, so there's always an arrow going up here. So this has basically taken my tree, semi-tree, and unrolled it over time. Okay? And every node in this represents a unique probability, right? A unique symbol sequence. And now, so every node in the trellis to the right represents a unique symbol sequence, correct? I can just use my forward algorithm to compute alpha for every node in the graph, in this trellis. So if I get 10 inputs, I'm going to get alphas for every possible symbol sequence for 10 inputs. And then I can just compute the alphas and pick the symbol sequence for which the alpha was largest. And now I have my most likely symbol sequence, right? What is the problem with this? It's going to blow up, right? It's a tree. With time, it's going to blow up. So here's where our heuristic comes in. So this was the forward algorithm. So, but here, anyway, so here's what we're going to do. One small thing, that there are two possible ways of generating a symbol sequence. You can also have a final blank, right? So if I want to compute the probability of a symbol sequence, I have to say alpha of S1 and alpha of S1 blank. Those two alphas would have to be added to give me the probability of the symbol sequence. That's one final little trick. But besides that, here's what I can do. This is the theoretically correct way of finding the most likely symbol sequence. But I want to keep it in, engineering feasible, right? So at the first time instant, I'm going to start and, remember, at the first time I could have a blank or an A or a B, right? So I'm going to compute those guys at the first time instant. And then at the next time instant, I'm going to compute all the nodes which I can access from there, right? But then I decide on some beam with K, and I only keep the K most likely and delete the rest. The rest I set to 0, which is to say I delete it, right? And then so all the things that have been killed are dead. So how many did I keep over here? I kept the 4 most likely, right? I killed 3. And then those I'm going to expand again, right? And then I'm going to keep only the best 4. I'm going to kill the rest. Then those I expand again. And so at each time, I have no more than 4 active, or whatever you choose. It's not going to be optimal, but it's going to be better than greedy, right? And you keep track of the most likely ones and keep expanding them. Eventually, when you run out of input, you're actually going to find the symbol sequence for which you had the highest alpha. You just have to make sure that if you have the same symbol sequence and a version with the blank in the end, you have to add the alphas to compute the final score. So there's some pseudocode for this, very detailed pseudocode in the model in the slides. Take a look. It explains the beam search very nicely. It turns out that this very complicated algorithm can be written using like 60 or 200 lines of beam search code as I have in my slides. Or if you're Jer Chen, who was one of my smartest TAs, you do it with 20 lines of code. So, and it works just as fine and just as fast. And nobody understands your code, not even me. Anyway, but we'll post the code at some time. Anyway, so here's the story so far. Sequence-to-sequence networks which irregularly produce output symbols can be trained by iteratively aligning the target output and the time synchronous training. So, or alternately by optimizing the divergence over all possible alignments. Distinct repetition of symbols can be disambiguated from repetitions representing extended output of the same symbol by introduction of blanks. And decoding can be performed by best path decoding, which is greedy, right? That's not BW, it's greedy decoding. Or you can do the optimal decoding, which actually is based on the application of the forward algorithm to a tree-structured representation of all possible output strings. Right? Any questions? So in the next week, we're going to, just some caveats, skip the caveats, we're sort of done. Next week, we're going to be talking about models where the output doesn't have order correspondence with the input. And the output can in fact be longer than the input. So that's the final piece in this sequence on recurrent networks. Thank you.